I will present our modeling effort to analyze the 2019 Ridgecrest sequence with 3D dynamic rupture models. And I would first like to acknowledge my co-authors, and in particular Taufiqurrahman, who did most of the modeling associated with this work. So the last decade, I've seen several episodes of a multi-fault earthquake with devastating consequences, such as the Haiti 2010 or the Palu 2018 earthquakes. And it might be that the hazard caused by such kind of earthquake is underestimated. Therefore, it's important to analyze a past complex event to try to disentangle the rupture sequence, to assess the mechanical condition promoting their occurrence, or to identify a specific feature in the strong motion. But constraining the kinematic or imaging such a multi-fault earthquake is challenging due to enhanced non-uniqueness issues. And 3D dynamic rupture modeling allow producing earthquake scenario compatible with earthquake source physics and is rife enough to complement data inversion effort. And we here analyze the 2019 Ridgecrest sequence in the light of previous earthquakes that we modeled, including the 2016 New Zealand Kaikoura earthquake and the 2018 Palu Indonesian earthquake. So I would like to first present the typical workflow that we use for modeling this previous earthquake. And usually we can constrain pretty well the fault geometry based on the high quality of observable available. And we can assume that the fault geometry is embedded in the stress field with a regional stress variation, which is expressed as a stress tensor and which is usually not strongly constrained. So our idea is typically to run first static analysis to explore the range of possible stress parameter, that is to look at the magnitude of the shear stress and at their orientation and see which stress configuration is compatible with the rupture. Then we can run 3D dynamic rupture models, and we can try to constrain a few parameters that cannot be constrained by static analysis. And typically we will run SCEC which solve for seismic wave propagation with higher order accuracy. And this also allows for dynamic rupture boundary, and this support unstructured textural meshes, which allow to easily account for complex fault geometry. So for modeling Ridgecrest, we have the chance to have a highly constrained stress field constrained by community stress model. So we can skip the static analysis. So when modeling previous earthquake, we've identified some mechanical conditions that may promote rupture cascading. And one of them concerns the stress field, more particularly the stress shape ratio, which balances the principal stress magnitude. So in the case of the Kaikoura earthquake, where the stress field acknowledging transpression, and this allow resolving sufficient stress on extractive fault and also on low dipping stress fault. And this led to a complex rupture path along fault of varying orientation. During the Palu earthquake, we have a stress acknowledging transtension, and this allow rupture to cascade along strike slip fault, but also on normal fault. And during the Ridgecrest sequence, we also have a transtensional zone, but no normal faulting was involved. That is, the fault is instead conjugate. It combines right lateral and left lateral orthogonal fault. Another mechanical condition that may help driving cascading rupture is a strong frictional weakening. So it promotes rupture across fault of varying orientation. We can see it on the fault system of Kaikoura. If we increase the dynamic friction from 0.1 to 0.3, several faults have a much less pre-stress resolve. So rupture may cascade across less optimally oriented fault, and this is important. This is an important ingredient for Ridgecrest because the fault plane of a conjugate fault system cannot be both optimally oriented. Typically, optimally oriented fault is at an angle between 25 or 30 degrees with the maximum principal stress. So if faults are perpendicular with each other and the principal stress bisects the fault, then the angle might be around 45. So the Ridgecrest sequence offers a nice opportunity to learn more about conjugate fault system. It is exceptionally well recorded, and there's the presence of high quality community model that allow modeling this earthquake more easily. But assimilating the wealth of available data into a realistic model is also a challenge. And that's what we try to do in this study. And we try to answer the following question. So what set apart both events? So there are 30 hours in between. Which condition allows rupture of conjugate fault? How could the main shock break through the foreshock shadow? And also we are interested in the reactivation of the foreshock left lateral fault and to see if it's dynamically viable. And to answer this question, we try to build a realistic 3D dynamic rupture model, which incorporate the following ingredients. So we build a complex conjugate non-vertical fault geometry constrained by all this observable. And you can see that it has kind of an helical shape to the north, and intersect the high resolution topography that we incorporate in our model. So we also incorporate a 3D community subsurface velocity model, that's a CVMS 4.26, 2D community stress model, that's a Young and Oxon, and also we incorporate the stress shown from more than 1,000 years of major earthquake. That is so the co-seismic and post-seismic stress change that is expressed as a stress tensor, and once resolved into the fault system into current strength change, we can see that this creates an additional loading of 1 to 2 megapascal. And so our model also incorporate a realistic friction law with a strong velocity weakening, off-fault plasticity and attenuation. And let's have a look at our scenario of the foreshock, the Seal Valley earthquake. So it involved mostly two faults, F1, which is parallel to the largest fault of the main shock, and F2, which is perpendicular, it's a conjugate fault. And rupture is neglected on F1 and quickly branched to F2. Rupture terminates quickly on F1, but is able to propagate weakly on F2, then it gains momentum and break all of F2. Quite interestingly, in our model, the main shock fault are not triggered, so there's no branching. We can also check the dynamic stress at the main shock hypocenter and the increase of up to 0.8 megapascal during the foreshock. And we can see that a considerable part of the main shock is shadowed by the foreshock rupture. So our model captures surface rupture on the left lateral fault, F2, and no surface rupture on F1. So the surface offset is coherent, consistent with the previous inference. And overall, the slip magnitude is also consistent with schematic model. So we have a magnitude of 6.5, and the rupture is a bit faster than most inference, that is, rupture speed is about 2.5 km per second. Now let's have a look at scenario of the main shock earthquake. So it is nucleated here, and it starts with a bilateral rupture, which quickly is arrested spontaneously to the north. On the other hand, the rupture propagates to the south until reaching the cross section with F2, where rupture is mostly arrested, but not at depth, where it can continue to the south and rupture the south of F3. So quite interestingly, our rupture capture crack to pulse transition and also the activation of the fault F2, which might be enabled by the realistic friction law that we account for. We are also able to capture the shallow slip on F4, which is this fault parallel to F3, and it requires a slightly higher static stress drop than the foreshock. So using this base model, we can try to study the sensitivity to modeling a gradient. That is, we try to use a different community velocity model, CVMH, and you can see that the slip during the foreshock is a bit higher with a bit more extended rupture on F1, which is still buried. And during the main shock, there's a bit more slip close to the hypocenter. Most interestingly, the rupture is not able to cross F2. So it seems that there's a high sensitivity to the size of the rupture area on F1. We also try to remove the additional loading from the past earthquake. And you can see that in this case, the rupture is not able to rupture entirely F2, while the main shock rupture is quite similar without rupturing F4. And if we use a community stress model, different community stress model that is FM3D from Verdecchia and Michael, we get quite similar results. That is, F2 is only partially rupture, but the main shock rupture is very similar to our base model. So it seems that the rupture of F2 is highly sensitive to the initial collision. And using our base model, we can try to study specific feature of the earthquake. That is, for instance, what Nico Schliwa during his master thesis, supervised by Alice, Gabriel, and Taufiqurrahman did. So he tried to study, to incorporate a low-latency zone into the base model in parameters like the flow structure with property based on Q et al. And it shows that the impact on accounting set fault zone on the rupture characteristic is small. That is, the rupture is not significantly slower. On the other hand, and these are quite preliminary results, it suggests that the impact of the fault zone on ground motion is quite important and not limited to the vicinity of the fault. So we have some high difference also at distance up to 50 kilometers to the fault. So in conclusion, we have a model, we are able to get a realistic data integrated scenario, integrating many of the available data, and it offers new insight into the dynamic of conjugate fault system. So if we assume a statically strong and dynamically weak fault, we can resolve sufficient stress on the rupture fault and reproduce this rupture sequence. So during the foreshock, we have rupture branching and simultaneous rupture, which is enabled by the epicenter location very close to the junction, as also proposed by Fukuyama in 2015 by studying conjugate fault earthquake in Japan. And the F2 fault F2 is very critically stressed. The stress shadow associated with the partial rupture of F1 during the foreshock is compatible with observed main shock rupture. And we are able to explain the reactivation of fault F2, which is naturally captured by the realistic friction law assumed. So we have a base model that can be used to study specific features, such as the role of crossfall, for instance, and the workflow can also be used to design realistic scenario of the earthquake. Thank you.